A very good afternoon to our session chair, Professor B.B. Officer, our keynote speaker, Professor S. Bukkapatnam, and all our esteemed guests. I am Manisha Singh with our vibrant group. Welcome you all to today's keynote talk to be given by our keynote speaker, Professor S. Bukkapatnam. So, our keynote talk at All India Manufacturing Technology Design and Research Conference 2023. Our keynote speaker, Professor S. Bukkapatnam, is a professor of industrial engineering at College of Engineering, Texas, A&M University, USA. He is going to give us a talk on AI-driven cybersecurity assurance in smart manufacturing. Now, without any further delay, I would like to invite our session chair, Professor B.B. Officer, to give us a brief biography of our keynote speaker and effectively take us through the proceedings. Please give a warm round of applause for our session.
Thank you so much. As we mentioned in the inaugural session, we have keynote speakers invited. They have traveled far and wide. They are here, and one among them is Professor Bukkapatnam. He is with the Texas A&M University. His master's and PhD degree he obtained from Pennsylvania State University. He is currently serving as the Rockwell International Professor in the Department of Industrial and Systems Engineering at Texas A&M. His research focuses on high-resolution nonlinear dynamic information for wireless MEMS sensors. He is in the domain of smart manufacturing and also working in the area of nano manufacturing. So that doesn't limit an engineer to work in the biomedical domain, so he has some work in the cardiorespiratory processes as well. He has over 151 peer-reviewed publications, couple of patents in the pipeline to be awarded soon. He has supervised 14 PhD candidates and a huge funding of $5 million from the National Science Foundation, the US Department of Defense, private sector. He also has close to 20 best paper poster recognitions, and he has been recognized with Oklahoma State University Regents as a distinguished research Halliburton Outstanding College of Engineering faculty. There is so much about him. So, and we are truly honored, as I'm reading this, and privileged to have you, IISc Boeing Technical Innovation, IISc Elgin Outstanding Young Industrial Engineer. I think it deserves a big round of applause. SME Daughtry Outstanding Young Manufacturing Engineering Award was conferred on him. And he currently serves as the editor of the IISc Transactions, Design and Manufacturing. And today he is here to speak to us on smart manufacturing, and we heard our chief guest speak on the Industry 4.0 revolution and how the world is connected today. And when machines interact with machines and machines interacting or responding to the environment, some amount of intelligence is built into this, and then there is always a concern, a threat, how safe we would be in controlling, or they would rather control the processes if they have the inbuilt AI. So he's going to speak to us on AI-driven cybersecurity assurance and smart manufacturing. So we request you, Professor Satish, to give this presentation. Yeah, please.
Thank you, Dr. Vijay. It was a very warm and kind introduction. And thank you, everyone, for being here to lend your ears for some of the thoughts that I wish to share with you. As mentioned, I will be discussing the topic of cybersecurity for the emerging smart manufacturing systems that will be part of the Industry 4.0 and beyond. And in this presentation, I would like to keep it what I call as semi-technical. I would like to share with you the import of the problem of cybersecurity in smart manufacturing, and then discuss some of the specific challenges that arise in this context, and then provide some glimpses of some of the ongoing work in our lab in specific towards addressing some of those challenges. So, overview followed by 2 specific case studies that may be of interest to us. So let me begin with the overall motivation. Why, as researchers and budding researchers, we should pay attention to cybersecurity in manufacturing? The answer actually comes from the cybersecurity domain itself. 3 years ago, IBM published a particular paper that talks about cybersecurity across various industrial sectors. According to them, manufacturing poses the highest challenge for cybersecurity. And as you can see in terms of numbers, the market for cybersecurity solutions in the industrial sectors, they call it industrial cybersecurity solutions, is growing at a very fast pace. It's growing at about 15% every year, and it's supposed to reach $40+ billion market by 2029. So it's basically a major deal. And one of the things that holds the country that I currently belong to, the United States and India, is basically the cybersecurity of our national assets getting threatened by basic foreign industrial actors or foreign governmental actors. Right? So that is something that US is extremely seized of. And we are focusing heavily and we are investing heavily in addressing cybersecurity in our industrial and manufacturing sector. And what makes this challenging? Compared to many other domains, manufacturing goes beyond IT. If you look at financial sector, if you're looking at, take any other sector of import, you probably will have one or a couple of the possible types of flows involved. In the IT sector, essentially it's data flow, essentially the network, right? So all the things that original cybersecurity world is focused on is securing the networks and securing specifically their IT networks. Next, you probably are familiar with cybersecurity of the energy sector, right? So there, they are looking at the flow of data as well as energy. But if you look at manufacturing sector, there are 4 different what we call as cyber physical flows. Essentially, you have the material flow. The material could be interdicted and then it can create issues, even at the cyber level, right? So basically something may be present, whereas your IT system may be saying that it's something else. By interdicting the material, you can actually make your system artificially starve or artificially block. if you know what manufacturing system starving and blocking are. So essentially, more material than what is needed would be present, or no material would be present. So essentially, by interdicting or playing with the material flow, you can create a havoc. And of course, the quality, the way the process interacts with the material can be affected essentially by focusing on or basically attacking the material flow. Similar to that, the common information flow, basically pertinent to the IT system, is again can be vulnerable. And two other kinds of flows that we need to be focused on is energy flow. Again, you can attack the energy systems. For example, you can attack the face of your electrical systems to create all kinds of issues from manufacturing standpoint. The last one, and but not the least, is the human. In fact, some of the worst accidents of cyber-physical nature happen because of the human actors. How many of you have heard about Stuxnet accident? Stuxnet was a major accident of the nuclear plants in Iran. Stuxnet accident happened because the intelligence agencies snuck a human actor who went through multiple cycles, basically like a human actor after the actor, after essentially human actor flow, with which they were able to reach the impregnable or presumably impregnable network of the nuclear plants, and then made their centrifuges operate at anomalous conditions to a point where they became unoperational. This happened more than a decade ago, right? And that was one of the headline cyber attack, and it happened because of a human actor. So what sets a manufacturing system apart is cyber vulnerabilities or cyber physical vulnerabilities can arise through 4 different flows. And that's one of the reasons why the cyber security domain considers manufacturing as the most challenging domain. And when it comes to manufacturing, the challenges pervades the entire manufacturing system. Of course, there are 4 different flows I would like you to remember, and these 4 flows pervade the entire system from the design, production, and all the way to the supply chain. Right? And there are many challenges. What I would like to do in the remainder of this talk is to give some glimpses of the challenges that arise across different domains. And we are working on multiple such challenges across different domains of the manufacturing system, looking at the design, production, as well as the larger enterprise. And when we look at the design phase, it basically looks at the data flow, information flow, as well as the intellectual property flow across the design through process planning stage. The production stage involves looking at the security of your machine as well as the manufacturing processes. At the enterprise level, everything else, logistics, transportation, etc. Right? And in the remainder of this talk, I will just focus, keeping the spirit of this conference on the production phase. How can we secure the manufacturing factory from major cyber attacks? And what are the vulnerabilities that we need to consider as we begin to secure these manufacturing power plants? And third, and probably more important, is how can we leverage the emerging AI to help us with securing these manufacturing power plants? So this is basically the theme of the remainder of this particular talk. In this particular context, we are focusing on 2 different specific challenges and solutions. One, we will be looking at the factory controllers or the machine tool controllers that you find. Second, we will be looking at collaborative robotics and environments and looking at the challenges and securing them. When it comes to cybersecurity, we look at what we call as cybersecurity taxonomy. This taxonomy captures the entire, what we call as 100,000 foot elevation view of manufacturing cybersecurity. This taxonomy has 4 components. The first one is what we call as the why component. Why should someone want to attack a manufacturing system? Second, we call as how component. What are the different modes with which they could attack? And what are the types of attacks that take place? The third is what we call as the where issue. So, which part of the manufacturing process chain would these attacks take place? And fourth are the countermeasures. What are the ways to address some of these cyber security challenges? In terms of the why question, so-called the attack goals, there are only 3 reasons why an actor would attack a manufacturing system. The first one is piracy. They want to take information, or they want to take some of the resources out of the manufacturer. One of the key types of attacks you might have heard about is what is called denial of service attack. What they typically do is they basically get hold of your IT or some kind of flow in the manufacturing or any kind of a system and demand a ransom to releasing it. So that is one of the major aspects, basically like pirates. It's piracy. Second is sabotage. It's basically something that most of the so-called competitors, both at the industrial level as well as the governmental level, they are interested in. Their basic goal is to destroy that particular factory floor or that particular operation. And third is counterfeiting, or basically duplicating. So basically what they try to do is they kind of change the flow without the knowledge. Basically that's a surreptitious change of the flow, so that the customer thinks that they are dealing with the manufacturer, but they are actually dealing with a duplicate. So essentially, there are essentially 3 goals for doing any kind of a cybersecurity. And the modes of attack, how they can attack, can vary depending on the basic capability as well as the motivation of the attacker. Denial of service is one thing that I just mentioned. Reverse engineer is something that typically used for duplication. Tampering. Also the side channel leak, which is an important thing that most of the factory floor cybersecurity experts are concerned on, and maybe covert channel as well as IP theft. These are basically the various kinds of attacks that you need to be worried about. In this talk, I just wanted to kind of throw these names so that we are all aware of it. And the remainder of this talk, I'll basically touch upon 1 or 2 so that we'll see how these attacks manifest, and we can look at what are the ways in which people are looking at in addressing them. Right? And as I mentioned earlier, where this attack takes place, it pretty much pervades the entire manufacturing system. And in particular, in the design phase, the focus is on the IP. And in the manufacturing phase, typically the focus is on sabotage. And in the enterprise level, the focus can be varied depending on the specific node of your entire supply chain. And also in the manufacturing domain, it's the more automated, the more digitalized your manufacturing plant is, the more vulnerabilities. So as a result, how can you create the most secure manufacturing system? Basically by disconnecting it from the internet. That's what they say. But that's becoming less and less realistic now. So we have to look at countermeasures. And there, I'm going to kind of add a few more jargons as well as introduce some new names here. Watermarking is one technique with which you can prevent some of the attacks on your factory floor controllers. And there are methods like authentication. Authentication is part of what we do in the IT networks. When you log in, enter your username and password, you are essentially authenticating. So essentially you can do that for every floor, not just the IT floor. And similarly, you can actually use noise injection as a means to confuse your attacker, and as a result you can actually save yourself from bearing the brunt of a cyber attack. And actually there are other methods like fingerprinting, obfuscation, and then anomaly detection. Probably just need to know these by names without knowing in the full details at this stage. Given the time, I'll focus on a few important ones, and especially the ones that we are actively studying. The next thing is attack vectors, basically how these attacks take place. If historically, sabotage, basically aim of destroying a manufacturing operation, remains the main goal. In other words, the attacker's main objective is to basically destroy a plant. And the objective could be to disrupt the operation or even destroy the operation. Disruption can lead to loss of quality, loss of productivity. And damage essentially can lead to various severity of safety compromise. It could be simple thing like a worker getting hurt, or the worst case, as it happened in North Carolina a few years ago, the entire factory can actually be blown up. So these are all possibilities that can happen because of cyber physical attacks. And since our focus is on the factory floor, essentially there are two main countermeasures that we need to be aware of. The first one is watermarking, and second one is anomaly detection. The watermarking is something new for the manufacturing community. It has been used in the other domains, especially the IT network as well as energy networks and so on. And anomaly detection, interestingly, is something that manufacturing domain has been adept at for the last several decades. And what happens in the anomaly detection is using the same kind of data sources with which you look at anomalies for the machine as well as the process for detecting cybersecurity compromises. Right? So essentially, you're looking at these two countermeasures. And I will try to present one case study for each of them. And what I will do is I'll spend much of my time looking at the first case study. And if I get done early, I'll try to spend some time on the second. Okay? So the first case study focuses on cybersecurity of the shop floor controllers. Right? When you look at the manufacturing domain, as I mentioned earlier, there are three areas where cybersecurity compromises, vulnerabilities can happen. And among these, client floor, factory floor has not received much attention. Just to give some data points here, about 4 years ago, the United States pumped in about $150 million to establish a center focused on manufacturing cybersecurity. It's called SciMani, and it's headquartered at University of Texas at San Antonio. And then it partners with various different universities and national labs, especially the Oak Ridge National Lab in Tennessee. Okay. And the work during these past few years heavily focused on securing the design phase, that is, securing your IP. Although sabotage remains the #1 attack mode, it has not received much attention. And the US government as well as the research community is beginning to look at this challenge. And this may be one area where the US and India can partner, because I'm pretty sure India has a similar kind of a challenge with respect to cybersecurity. And factory floors are one areas where there can be a major vulnerability, at the same time a fantastic opportunity for cross-pollination as well as so-called secure hardening. And as I mentioned, it's not just India, US. The cybersecurity vulnerabilities have been reported across the world. It didn't spare a developed, developing, and so on. In fact, the more developed and more advanced you are, the more vulnerable that particular country became for cybersecurity attacks. Just to give a few examples here. The first one happened about 10 years ago in German steel mill. And it basically had led to the blast of the entire furnace. And at this, basically there is some kind of loss of life that happened in the 2014 accident. And people suspect that the type of attack that actually led to this accident was an injection attack. So basically, an actor injected a particular bad code that created this particular accident. And similarly, another kind of an accident, 2017 in Honda plant, led to the shutdown of that particular factory for several days. And more recently, we heard about closure of an entire port and port operations, which is key element of the supply chain, for 3 to 4 weeks because of, again, the denial of service. And what is the common nature of these attacks? They are essentially cyber physical in nature. They are not just simple IT attacks. Right? So essentially they are attacking either IT system to kind of target or create havoc in the physical world, or they basically are coming to modify the physical world by sending bad material or bad actors, human actors, to destroy the IT networks and beyond. Okay? So these are a few examples. Essentially, as you can see in this slide, it can lead to human loss of the entire plant, literal catastrophic loss of the plant, shipment delays, financial impacts. These are all the consequences, ill consequences of these types of attacks. And the minimal consequences essentially are poor quality of the parts. But people are more worried about the safety and plant failures, which can have more devastating consequences. And that remains the challenge at hand. And a lot of researchers and research groups as of today are trying to tackle the various modes, or basically various vectors of attack, and looking at solutions that would be practical in those contexts. Okay. And when you look at the factory floor, because of the era of automation that has just passed, we have most of the factory floors having machine tool controllers, SCADA systems, and so on. In fact, even if your particular favorite factory does not have one, the chances of it having one is growing at the rate of 15% every year. In fact, within the US, 9 out of 10 factories are belonging to the small or maybe semi-medium companies. Even for them, 7 out of 10, basically 70% of small manufacturers have automated plants. So they have factory floor controllers. And the worst part is the following. Many of them are suppliers to the major companies. And many of them cannot afford major cybersecurity fixes. So they are the most vulnerable, small businesses who have automation. Okay. And what do these automated systems have? Most of them have what is called machine tool controllers. Something similar to what you see on the screen, right? If you have any kind of a CNC machine or any kind of an automated machine, you have to deal with these controllers. And these controllers are highly vulnerable, and right now watermarking remains the major, if not the only way to secure these controllers from various kinds of cyber attacks. And I'm going to change the gear a little bit. I'm going to go a little bit technical, and then I'm going to go a little fast. But we can always come back and then answer some of these things in the Q&A time as time permits. Right? The watermarking is something that actually is borrowed from a different domain, and it was pioneered by my colleague Professor P.R. Kumar, a National Academy member from Electrical Engineering Department at XCM. And it was applied to various different domains: power plants, autonomous vehicles, and electric grids. So far, we did not see that, and we basically tried to adapt that for manufacturing, because that is a solution needed to secure these machine tool controllers. It's not just a fix, but you can actually guarantee the performance, and you can tell how well it will perform in your domain, both in terms of delay, how long before, in other words, how long after an attack you are guaranteed to detect your attack, so that you can, the delays can be dangerous, right? So sometimes milliseconds, sometimes seconds. And second is how well you can detect, what is the probability of you missing those attacks. You can actually provide this so that you can provide all the risk measures. And in terms of idea, it's very, very simple. Essentially, if you look at a manufacturing system, something comes in, that thing that comes in can be in the letter U here, essentially input to your manufacturing system. And Y is your state, or it could be the output. Typically, what we look at is Y is basically the thing that you measure from your sensor, and U is the input from your controller. So if you have a machine tool controller, U at every time is basically the control signal, and Y every time is basically the position as measured by your optical scales and so on. And W is some noise that's present in there. What dynamic watermarking does is very, very simple. It basically adds a watermark E of t at every point in time. So what it does is it tries to modify the control signal just that little bit, so that you basically look for the presence of this watermark while you are getting the data from your sensor. So let me kind of repeat to make sure I'm properly understood here. In a typical machine tool controller, what you do is you send a control input U, and you get the position measurement or whatever, Y of t at every point in time. And the evolution of how you give the input and how these measurement changes is captured by a simple dynamic equation. Y at time, where your machine position will be at time t plus 1 is dependent on where the machine was at time t, that is Y of t, as well as the input that you give. And the input that you give, that U of t, is basically based on this PID control and other things that you build into the machine tool that you may be aware of. Right? I will not get into the detail. But what we do in the dynamic watermarking is we add this extra watermark E of t to the control input that you give, so that it becomes the watermark very similar to the watermarks that you typically see in your documents. So what do you use the watermark for? You basically check for it, right? Check for the presence of it. So that's exactly what we do. Right? And the beauty of giving that type of a watermark is you have two guarantees. One is the persistence guarantee, and second is the variance guarantee. So essentially these are all mathematical concepts, and statistically you can develop some simple statistical rules based on the numbers that you are getting to verify whether the integrity of your controller is present. Why is that important? The data from the sensor can be obfuscated, and then a wrong input can go to the controller. Right? And similarly, the data from the controller into the machine can be interdicted, and a wrong data can be sent to the machine. Either one can create a problem. Right? So, by doing this checking, what we kind of guarantee is from the data, we are checking to make sure the value of the inputs remain within a particular bounds. And as long as they are within the particular bounds, we basically tell that the machine does not have an attack on its controller. The moment the values that you are getting, this D and T, go out of the bounds, be above a particular statistically determined threshold, you basically say that there is an attack. Okay? So it's a simple idea. So all that you're doing is putting some watermark and basically collecting the data and checking that particular two values that you can compute from those numbers. As long as the values remain within a threshold, good. If the moment they go out of the threshold, you basically say that there is something wrong. Simplistically, that's what it is. Right? And there is a theorem that basically says that if you just do what I just told, like inject those watermark and check them, only way an attacker can get away from an attack is if it becomes a so-called non-attack, that is zero energy attack. So if the attack actually has any effect, you should be able to detect it at very high guarantees. And as I noted earlier, this attack can take place at multiple locations. You could secure the controller by checking, by watermarking the controller, or you can actually secure the sensor by watermarking the data from the sensor. So essentially, watermark one and check on the other, and vice versa. Right? And this is basically the outline of this watermarking, and we basically validated on two different domains. The first one is actually a smart manufacturing platform. And one of the things that I wanted to share with you is this, what we call as smart hybrid manufacturing platform. Right? Since I'm Indian, I'm going to give some historic perspective. Growing up, I heard stories that Mahatma Gandhi wanted every house to have a charkha, right? So that everyone wants to become self-sufficient. Every village should be self-sufficient. I may be paraphrasing, but that's pretty much is the message that we got growing up. What could be the general purpose Swiss knife of a machine that can be pertinent in the modern and emerging context? That is a smart hybrid machine. Smart hybrid machine is capable of working on multiple materials, and it actually can embed multiple processes on a single machine. It can 3D print, it can machine, it can measure, it can actually heat treat, and also it can polish and do those kinds of things on both metals and ceramics. So it actually can, it's basically like a multi-purpose machine. The capacity of the machine basically will tell you the kind of parts you could make and then the kind of materials you could handle. So this is basically considered as one of the up-and-coming platforms, especially for this emerging smart manufacturing era. And this machine, as I mentioned, has the ability to mill, grind, basically directed energy deposition through laser, as well as it can actually do in situ measurements and so on. And this machine that we actually adapted, basically we modified the machine so that we can get 14 different channels of data. So it's basically a heavy duty data ejector, and it has some very, very complex control loops. So it's basically one of the nice platforms for us to study this cybersecurity. And the animations are not going, but what I would like to kind of point out is it can simultaneously gather data from 14 different channels. So as the process is happening, 3D printing, machining, doesn't matter. You can get the forces, temperatures, etc. of the process as it's going on. And you can get the data at so-called megahertz frequencies. So in other words, you probably are getting gigabytes of data within a minute, right? And you can use this data gainfully because you have data about what you hear, what you see, and so on, right? So you can actually use it for various types of operations that you see on the left-hand side. You can actually use it for materials discovery, and on the flip side, you can actually use this type of a platform to gain a good understanding of the cybersecurity. If you can secure a process of this kind, you basically are on your way to securing many of the manufacturing factory floors, because this is basically one of the challenging moments. And you can actually play with different kinds of materials, and more importantly, it has one of the more challenging and involved control loops. And luckily, we have been working or toying with this machine for some years, and this is the platform for which we are studying the cybersecurity. And this is the main platform for our multi-million-dollar project on manufacturing cybersecurity that we are working with our colleagues in electrical engineering as well as from other universities who have interest in manufacturing cybersecurity. But as you can see, we love this machine too much to a point where we don't want to put the cyber attacks on the machine alone. So we create a digital twin. So essentially we take the data, and with connectivity to our cybersecurity as well as smart manufacturing groups, we create a data pipeline and then create an interface. Again, I'm sorry that animations are not playing here, but we have a major data pipeline with which we can build the digital twin using the data that emanates from the machine at very, very high rates and volumes. Again, shifting the trend a little bit, the essential manufacturing controller is typically a closed system. If you go to any kind of machine tool and look at the controllers, they have what are called closed architecture. Be it Siemens, be it Rockwell, doesn't matter. You basically, most of the commercial machine tools, they don't diverge their architecture. So what we typically do is, you have to probe the machine tool and learn their operation. What you're doing here is very simple. You provide an input to your machine tool and then collect the data as you are running that machine tool operation. And based on that input-output relationship, you are trying to understand the architecture of that particular controller. So to do that, what we did is a simple operation that you see on the right-hand side, bottom right-hand side. We basically made the controller move a simple XY path. And as it executes that XY path, we are looking at the data from the various channels. One of the channels is basically the actual positions and actual velocities that you can actually pull out of a machine tool controller, right? Using what are called OPC vehicles. And based on the data that we get for the actual Y values for different kinds of the requirements that we want inputs, we can actually reconstruct the entire machine tool architecture. So what we have done without too much elaboration is we basically look at the entire architecture, probed it at different locations, and based on that, again, where I didn't need animation, it shows. Okay. Essentially, like, I'm going to go very fast, please bear with me. Essentially, we constructed a digital twin consisting of about 34 parameters of different kinds of a machine tool controller. This actually was validated on the Siemens controller of the hybrid machine. Now that we have a reasonable controller, essentially where all these parameters were obtained purely through machine learning, we use this digital twin of the controller for studying the effectiveness of the various kinds of watermarking techniques on the performance of your controller. So I'm going to shift. Yeah, for validation studies, we consider two kinds of attacks. So essentially what we did was, we consider two kinds of attacks here. As you can see, there is this A is basically the attack that comes in, and then to secure the controller, we added this watermark E. So essentially the attack is something that we introduce into the digital twin, and then E is basically the watermark again we introduce into the digital twin. And what we do here is we run the various kinds of trajectories and then look at how these attacks would modify those trajectories, and without and with watermark, how we can see the difference in the way the machine tool behaves in terms of being able to withstand this particular type of an attack. Right? And again, we consider only two types of attack. The first one is the injection attack that I mentioned earlier, that destroyed that steel plant. The second is the replay attack, where it basically tries to duplicate the control. In the case of injection attack, we kind of provided different kinds of noise levels and then see how this noise level will destroy the motion patterns. And the replay attack is basically we kind of take the controller and then believe that something that happened in the past or something that doesn't happen today or at this moment is what is the actual trajectory. So essentially spoof the entire controller into believing something else is happening. In the case of injection attack, we basically attack causes some kind of disturbance. Basically what the disturbance essentially means is, if you're thinking about a cutting tool, the tool is basically, instead of moving this way, it's basically scratching the workpiece. Right? It's going to create a lot of quality issues at the very least. And what happens in our case, once we have the detector turned on, when you have normal operation, when there is no attack, the values are well below the threshold. So pretty good. The moment you have this attack in place, within a short period of time, the D and T values that are introduced, those mathematical terms, those values jump above the threshold, giving you basically the alarm that the system has reached a point of threshold, which means there is an attack that's underway. Not imminent, it's underway. But as you can see here in this plot, if you look at the bottom two right, the first one is the D statistic and the right one is the T statistic. In this particular case, T statistic is better off in terms of being able to detect the attack at the shortest time. D statistic could do it, but it's kind of very little bit below. By that what I mean is T statistic immediate. Like the moment the attack starts. D statistic slightly below. And essentially you have these types of scenarios that you can play with under different kinds of attack levels and severities, as well as different designs of your watermark. The research is still on. There is a still open question, is what is the right watermark that you need to place to obtain the best kind of security of your controllers from these various kinds of attacks. If there are interests, we will discuss this further. And similarly for the replay attack, the same kind of scenario. Essentially, you basically can have multiple modes of attacks, and then in this particular case, these statistics seem to do a little bit better, as you can see. Right? So there are various types of attack modes and different kinds of securing and detection mechanisms. And we actually did it on not on the hybrid machine, but we took a simple stepper motor, and then we studied the entire dynamic watermarking and its performance on securing this stepper motor. And for the stepper motor, we basically have three basic stages of securing it. Basically, we're studying the thing by first identifying what is the dynamics of this, so that you get this y of t plus 1 equal to a plus a of y of t and so on, that equation. We can build from the actual data, and then we do the right watermarking, and then study the performance of the watermark under different attacks. Here these are all real. Right? So this is the data from the controller. I'm going to be very fast given the time. So essentially the same equations, so I'm going to skip the details. But the general message is the following. The higher the severity of the attack, the faster you can detect. Right? The lower the severity of the attack, the slower would this watermarking would be able to detect. So the idea here is to design the watermark in such a way that you are fairly confident about your ability to detect your minimal attack. So essentially, the stealthiest attack that you are interested in detecting should be detected by appropriate design of your watermark. And if not, you might be very delayed in detecting it, or you probably would not be able to detect until that particular attack creates the havoc. So that's one thing to note. And the second thing is about how do you design those kinds of attacks if you're going to be on the other side. The attack should be such that it needs to cause some kind of a damage to the machine tool controller. If it is below a particular threshold, there may be an attack, but it will not have any effect. Right? If it is well within the precision levels. So there is a nice game theoretic formulation that you can think about in terms of addressing the quality, the attack latency performances, as well as the dynamic watermark. That is just a thought I would like to leave everyone with. And other remaining things are basically the performances under different kinds of attacks. Earlier I talked about injection attack, in this case what is called flip attack, where it's not injection, but it's kind of very deterministic. It basically, whatever is plus, it basically makes the sign opposite. So when the tool is supposed to move this way, it basically makes it move the other way around and so on. Right? So again, the same kind of performance since we were able to get. The message is very same. The more severe the attack, the easier it is to detect. Flip attacks are considered to be highly severe, and the dynamic watermarking performs like a charm. Right? And the moral of the story is the following. Although the manufacturing floors are most vulnerable, historically speaking, securing the manufacturing floors has just begun. Even in the US, the communities are just seized of this matter. So those of us with interest should think about collaborating and then thinking deeply on this subject. And one of the things that seems to be of interest is dynamic watermarking. And there are lots of very interesting, deeper issues within dynamic watermarking that we can think in terms of designing this watermark as well as studying its performance. And third, interacting with the machine tool controller companies, Siemens, etc. Right? And also, for those of us who are entrepreneurial, basically there is something about building new generation of controllers with cybersecurity ground up. So, how can you build these capability of designing appropriate watermarks and so on, so that the controller as is secure. So these are some of the ideas that we can think about. And given the time, I will not talk about the second case study, but I would like to thank every one of you for being here and then being so attentive. I saw each one of you was just looking at me, so that was amazing, right? Sometimes I don't get that from undergraduate students. Again, thank you for lending your ears and being present, and I would be glad to take any of your questions at this point. Thank you.
Thank you for your great presentations. Regarding digital twin, how are you integrating the digital twin in your digital systems?
Yes. Right now we are using digital twin purely for validating our control performance, right? As well as studying the performance of the dynamic watermarking. In future, we are basically trying to create what is called live digital twins, in the sense that we basically can update the watermark as you go using the digital twin, so that you can put it into the physical systems or the controller later. But right now what I said later is purely theoretical, because 90%, if not all, the commercial industrial controllers are closed architecture. Only when we have open architecture controllers in place, you would be able to fully integrate your digital twins into a physical controller to be able to dynamically adjust these watermarks internally and quickly. Yeah, but a great question. Thank you. Yes.
What are the funding source for this cyber attack? Is it competing companies or competing countries? Please.
I would say all of the above. Yeah. In fact, that's what's happening. For small and medium companies, it's usually the competitors. For the major companies, as well as government cyber physical systems, it's usually the foreign actors. Yeah, right now you can think about the conflicts that are happening in the US. You can have candidate places from where these attacks are happening as we speak. No, actually, good question. Watermarking is something that you might have seen in your currency notes growing up. Okay? So when you kind of hold up your currency, you see a watermark. What is this for? It basically tells you that whatever the currency note that you got is authentic. Okay? That's exactly what we are doing. Watermarking has nothing to do with water, as far as I could tell. Thanks. So obfuscation is basically trying to what is called cloud the information. Yeah? So essentially if you look at any kind of a machine tool or any kind of manufacturing systems, they are distributed entities. Even within a controller, I showed two different entities. One is the sensor, that's basically telling where the tool is, and there is this controller that's basically providing some kind of electrical power so that the tool moves. So two different entities, right? So obfuscation is basically making one not know the actual state of the other. So basically, essentially cloud is the idea. Thank you for the question. Yes.
Thanks for the very informative talk, and this is very much helpful for our for PhD guys like us who are working in the manufacturing sector. So I wanted to ask you one question. So can we use the control charts for detecting these signals? And one more question is that if severity is higher or severity is lower, then detection can be done with the increase in the average run length, or we can, if we are increasing ARL, then it will be more prone to our manufacturing. Since we are selling more quality products.
Absolutely. Great questions. As you can see here in the chart, you basically helped me kind of go through the entire presentation, the other case study also. Not just within the controller, even for robotic systems, you can use some of the control charting scheme, as you see here on this chart, to be able to detect any kind of a change. So in other words, detection is essentially some sort of a process control, right? Absolutely. That's the first question. Second part is, again, as I mentioned earlier, it's the motivation for an attacker to make it as severe as possible without getting detected, right? And it's basically the motivation for your manufacturer to have as small a watermark as possible so that it doesn't disturb your normal operation, but still be able to detect the various kinds of attacks. Does that make sense? So it's basically like a conflict, it's basically a balance. So that's why a game theoretic formulation that doesn't exist as of now is a very, very tantalizing prospect that anybody would like to kind of indulge in.
Sir, one more question. So, if we are, in case of control chart, we told that we can detect out of going our sample. So whether that is belongs to that cybersecurity or our manufacturing input.
Yeah, great question. Yeah. So the question kind of, if I were to restate, if I see an out of control behavior, is it because of some kind of a faulty component of the machine, or is it because of the cybersecurity attack? Right. So that's the question. The answer is you should not care, because if something is going out of control, it's your job to kind of control it. Right. Then there are some kind of root causing diagnostic methods with which you can kind of go back and figure out the root cause as to whether it was due to the component going basically degrading, or is it because of an external attack that comes into place. And typically, when you have if you know the condition of any kind of component, despite that, if you're seeing some kind of an anomalous behavior, then you basically have a very high chance for attributing that to a cyber attack. Okay? I think I'm between you and your lunch, right? So
one more talk is there.
One more talk is there, so that's good. So in that case, again, with the interest of the time, should we kind of close this? Yeah, over to the chair.
Thank you, Professor Satish, for this wonderful presentation, giving us insights into altogether a new dimension of importance of cyber physical systems, and it all started with your mention of the IBM study and how important it is today to tackle this particular problem. And you also presented the taxonomy, the chart of the different types, the goals, and also the countermeasures of how we could use them, and then also suggested a method of experimentation, validation, also showcase the results. And so thank you for this wonderful, insightful presentation. You also mentioned that one of the conclusions that you drew were that the severity, if it's higher, faster is the detection. So how AI can help, in this particular aspect is one question, and then we can conclude with it. I had kept this question, I thought maybe.
Actually, right now the systems are entirely closed, right? So basically, you have an attacker who has a particular motivation. AI is the only tool that's available as of today to be able to discern the basic motivation of the attacker, as well as provide, basically learn and provide the optimal counter response to the whole kind of an attack mode that the attacker is indulging in. So in other words, behind every step that you see here is basically a machine learning module. That's number one, trying to learn and then understand the digital twin. Right? Because the controller is closed, you want to understand the controller, that's basically one machine learning. The attacker, their mode is previously unknown, so essentially you have to design the watermark right way so that you are having a particular kind of performance with which you can address this particular attack. And third, basically the collaboration. Essentially, what could be the dynamic game that you can play between the attacker as well as your system, so that you can kind of learn dynamically the motives of the attacker that may be changing, and then come up with, in real time, modification of your watermark so that you basically are secure from any kind of adaptations your attacker goes through. So in other words, AI in many ways pervades across every guts of the challenge that you're dealing with. I hope I'm serious.
No, you have covered that, but I said making it more clearly explicit to us. Yeah. So, big round of applause for this wonderful presentation, throwing new insights and new dimensions into the cyber physical system space. So, thank you very much.
Let's thank the
Thank you so much, sir, for such an informative now it's time to express our gratitude. So we have a moment towards a token of appreciation. So I would like to request Session Chair Sir to present that moment. Before we disperse, it has been an honor to be part of this talk. Thank you so much, sir. We are honored.